Sorry. So now it's okay. They can normally hear me. So of course, this change of index is very small. It's the level of, for instance, in air, 10 to minus 19 centimeter square per watt. So it means you need a huge amount of watt, petawatt, even more, to change slightly index of the medium. So the question is it the case in vacuum? That's the case in the medium due to this nonlinear coupling of the field itself with the medium, with the atomic presence in the gas, for instance. But what happens for the vacuum? And as you know, in quantum theory, vacuum is not empty anymore. There is fluctuation inside. The question is, so can the speed of light be modified, the index of the vacuum be modified when you apply also a strong external field to this vacuum? Before answering, of course, you will see the answer is yes, and that's the goal of our project. Before answering, I open a small parenthesis, and just to show that actually this question, can we modify the speed of light when we apply an external field, has been asked not in the case of electromagnetic field, but in the case of gravitation fields by Albert Einstein itself. And in 1907, he started with the question of is the speed of light still constant when you are in an accelerated frame, not an inertial frame, but an accelerated frame. It means, as you know, for Albert Einstein, in a gravitational field. And it's very interesting to see that his first paper was that he started doing calculation and realized that in an accelerated frame, it means in an accelerated field, or actually in a gravitational field, the speed of light is not constant anymore. There is some effects. Special relativity is special, very special, and restricted to a Galilean change of frame and not an accelerated frame. So then, as you know, from these first results, not well known, all of us, then he wanted to generalize the principle of relativity. And he found a solution to generalize that and to keep the speed of light constant by introducing this famous tensor metric with a curved space-time, where the speed of light appears to be always constant. And you keep the special relativity, you generalize it, with the price to introduce a curved space-time, what is the physical reality of this curved space-time? Nobody knows, but it works to generalize the principle of relativity. So in this case, vacuum disappeared. There is no more physical vacuum as we know it in quantum field theory, but you have a curved geometry and which predicts, for instance, as you know, that when you put a gravitational field, then you curve the space-time metric, and you obtain some effect like deflection of light, which is typically an effect of optical effect of deflection with a gradient index. But here there is no more a change of metric. And it was observed, this deflection, in 1990. It was the first confirmation of the theory of Einstein of gravitation, and it was a real success. But let me now speak about somebody else. Galileo would have said, "E più si muove," I don't know if I say it correctly in Italian, and as yet it moves. I mean, it reflects. So you can say whatever you want about the constanticity of the speed of light. It looks like if you are a kind of physicist and not a geometric theorist, but a physicist, then you observe a deflection of light and you conclude in a flat metric that it's like we are still in a flat metric, and physically the index of vacuum change with the gradient of index and the deflection of light. And actually, this second way to interpret the gravitation field and picture has been proposed by Wilson and Dickey, famous theorist Dickey, in 1957, where they show that actually the general relativity can be obtained in an Euclidean flat metric. So you do not try to cheat with metric, you keep a flat metric, but you introduce, again, you do not know the reason, but you introduce a gradient of change of the optical vacuum index, and with a gradient related to the potential of and you also need to include the change of the mass in order to preserve the equivalence principle. And just to show you, because then we will speak about that, the vacuum index. This vacuum index is strange for us, no? Vacuum index, and it's equal to 1. No, it's modified. And as already shown by Landau and Lifshitz in 1975, this is actually formally identical to the G00. And then one last comment about this interpretation of general relativity with the index, vacuum index gradient is an important feature pointed by Dickey at the same time in 1957. He then, at the end of his long article, he said, what about the value 1? I mean, okay, if I am close to a mass, a gravitational mass, I obtain an index gradient, but I'm far from it, it's in average 1. And is it constant in time? Okay, spatially it change, but in time, is it constant? And he said, if we imagine that as soon as I am transited to a gravitational potential, I change the vacuum index. But so now he used the Mach principle. I'm always sensitive to all the potential gravitational everywhere. And due to some potential delay, I'm going step by step to increase the horizon of this potential. And in that case, it's like I increase the index, the value of the index in time. And then we show that that explains what we call the cosmological redshift, due actually to the change of the speed of light plus the change of the inertia, which is very important, inertial mass. And just for advertising, we did a paper using this formalism from Dickey and try to apply it to the observation of the supernova. And so we are now in a flat metric, static flat metric. We do not use any modification of the metric, but then we, as Dickey proposed, we change the vacuum index, optical index, and the inertial mass, and apply it to the supernova, and we see that it fits perfectly the curves by introducing the change of the index in time as an exponential variation. So that was published in this paper. I give the reference if you want to check, to read it if you are interested. So now the question, I close this parenthesis of the optical index for the speed of light in gravitation and saying, okay, now what about the vacuum optical index in vacuum by electromagnetic? And that's exactly the inverse. You will see that there is no observation like gravitational fields. It has never yet been observed, but there is a theory, so which is the inverse. And the theory has been proposed by Heisenberg and Euler in 1936, starting not from the QED vacuum, but from the, at that time, the Dirac-C vacuum, which is very close, and applying the same idea from a medium, but with this vacuum field of Dirac-C, electron-positron, virtual pair in the vacuum, and saying, oh, okay, so if I apply an external field, then due to the nonlinear coupling of this external field with the studied electromagnetic waves, I should expect, due to the coupling with the virtual electron-positron pair in the vacuum, I should expect a nonlinear coupling as in medium, in matter. And they did such a calculation and published in the paper, and that's what we call the famous modification of the Maxwell equation found by Heisenberg and Euler. And they realized that the Maxwell equations are not linear anymore, and there is an extra polarization of magnetization induced by the quantum vacuum. And is not linear anymore, and with normally a change of the vacuum index when you stress the vacuum with intense electromagnetic field. And as you know, this parameter is very small. You need about 10 to the 29 joule per cubic meter of electromagnetic field to change by 1 the index. Just to show that now it's a very standard orthodox result. It has been derived result by Schwinger in 1951 using the what we know today, the QED frame, and published, obtained the same result as calculated by Heisenberg and Euler. But now the interpretation of a coupling of a photon-photon coupling, like this Feynman diagram. So, in conclusion of this first part, we can conclude that at least in QED frame, theoretical frame, the speed of light in vacuum should be reduced, and even at macroscopic scale, at the space scale of your external field, in a classical optical sense, when you stress the vacuum with intense electromagnetic field. And just to finish, this by Schwinger is one of the 3 famous papers of QED. And this is the one where he focused on this idea of what happens when I apply an external macroscopic field. And in this paper, of course, he predicted the anomalous magnetic moment of the electron, and also the change of the Maxwell equation, which becomes nonlinear, again, at macroscopic scale. Means if I apply an external field, normally, due to its coupling with the electromagnetic wave I study, and I predict some modification of the vacuum index, optical index, and vacuum speed of light. So only few experiments and physicists who try to observe such a prediction, because it's a very important one. It's, I mean, a behavior of a change of the quantum vacuum at macroscopic scale, the change of the fundamental level of vacuum. And today, the most sensitive search has been obtained by looking for birefringence of vacuum. And the best sensitivity has been obtained by the experiment PVLAS, which is now finished, but was running in Italy. And the basic idea is to apply an external continuous magnetic field in one direction inside a Fabry-Perot cavity. And they try to, in this case, you expect a change of the vacuum index or vacuum speed of light in one direction, polarization direction along the magnetic field. And it means you predict a change, a vacuum behavior, a birefringence behavior of the vacuum because of the change of the index in one direction. And so they try to the polarization of the laser through this chemical. They never observed a signal. They reach a sensitivity about 1 order of magnitude below the expected QED signal after 100 days of accumulated data. And they are today limited by the intensity of the field. There is one other experiment very interesting for us, the DeLLight experiment, proposed and performed by Jones, British physicist, in 1960, who tried to do what he did. He built a prism with a coil, a standard coil, and with a shape of prism, with a coil, and apply a magnetic field of 1 Tesla. And inside and outside, of course, there is vacuum. And he said, okay, now if I switch on the current, I apply the field, and normally I change the index of the vacuum and the speed of light inside my prism. And in this case, I expect some deflection. He tried to measure a deflection. He reached a beautiful sensitivity, very impressive sensitivity of 0.5 picoradian. Unfortunately, he didn't observe any signal because at this level, 1 Tesla, the expected deflection is only 10 to minus 23 radian. So 6 or 7 years ago, we with a fantastic laser, which is a LASERIX laser. They deliver very intense laser pulse of femtosecond pulse. So the duration is 30 femtoseconds at very high intensity, 2.5 joule per pulse. Voilà. And if you focus such a pulse in 5 micrometer transversal width, you obtain an intensity of the level of 10 to the 20 watts per centimeter square, which correspond to a field, a magnetic field, for instance, of 10 to the 5 Tesla. So our idea was to say, okay, let's try to do such an experiment by Jones, try to observe deflection, but using a field produced by the laser pulse itself. In this case, we increase by a factor of 10 to the 5 the available magnetic field. So it means the effect of nonlinearity in vacuum of 10 to the 10, like the square of the field, the intensity of the energy of the field. So that's what we now call the DeLLight experiment, deflection of light by light. The basic idea is what we call a pump probe experiment. So we start with a pump here, a pump pulse delivered by LASERIX. So as I said, 2.5 joules, 50 femtoseconds, focus in 5 micrometer transversal width. And at focus, this pump produces a gradient of index inside vacuum because of nonlinearity of QED. And it means the gradient proportional to the intensity of this. And there is a second pulse, what we call the probe pulse, which cross this modification of vacuum here. And at the same time, and normally, so which cross this gradient of index, and the waveplanes are then refracted, as usual. And then after focalization, this probe pulse is deflected due to this refraction by a very tiny angle. So using the LASERIX laser specification, we expect from the QED calculation a deflection of the level of 0.1 picoradian. It's a very tiny deflection. So the idea is to measure that by interferometry, because we use a standard direct deflection method. It's a very tiny deflection. So we try to amplify it using an interferometer method. So this interferometric method is based on the use of a Sagnac interferometer. So what is a Sagnac interferometer? It's a closed interferometer. So you have here which enter inside Sagnac interferometer. Half is an emitter, half is transmitter, and both are reflected by two opposite mirrors and come back and interfere again in the same beam. And can show that here in this output, that the dark output and the two pulses are in opposite phase, and you obtain an extension with, of course, a residual intensity profile, because your Sagnac is not perfectly symmetric, with a residual interference profile here, limited by the extinction factor, which is the ratio of the intensity in the output divided by the intensity entering inside the Sagnac. And this extinction factor is limited by the symmetry of the pair in reflectivity and transmission. So here, parameterized by a parameter delta R, we are used to for this notation, and also par a residual possible phase difference to misalignment of the optics, surface defect of the optics, and eventually so now, so the idea now is inside one arm, in order to focus both the front and the inside. And in the same time, with the front pulse, we focus the pump, right? Intensity pump pulse, which modify the vacuum and modify the speed of light in order to reference the front, which is time coincidence with the pump. The reference arrives either before or later, and when I say before or later, it's like a few hundred picoseconds. That's enough. Huh? 1 millimeter, it's enough to be out of time. And then the advantage here you have the deflection corresponds to of the beam. And this small displacement, delta y, it corresponds to a displacement of the interference intensity profile in the dark output, which is amplified by a factor A, which is, we can show that it's inversely proportional to the square root of the extinction. So higher the extinction is, higher the transversal displacement of your interference will be high. So the goal, as we will see, is to reach an extinction of 510 to the minus 6, which corresponds to an amplification factor of about 250. And then switch on and off and alternate one measurement with the pump on, one measurement with the pump off, and try to observe a shift, the displacement of the interference signal. So such measurements are done at 5 Hertz, because I forget to say the repetition rate of the laser is 10 Hertz. We have 10 pulses per second. So let's see the expected signal again in the QED theoretical frame. And this displacement here is the formula, but what is important is that, of course, it's proportional to the energy of your pump pulse. So for LASERIX, it's 2.5 joules. And it's inversely to the square root of the extinction factor, as we said, and inversely proportional to the cube of the waste of the beams, probe and pump beams, at focus. because of course, smaller is your beam, higher will be the intensity of the pulse, and higher will be the deflection. So using such a goal value of 2.5 joules, that's the LASERIX installation, then with an extension of 2 to -6, so that the extension we can reach today with the prototypes, and focusing at 5 micrometer. Why 5 micrometer? Because it's a typical reachable value for in optics with such a laser. We expect a deflection signal after amplification of 15 picometers. So the idea, of course, is to stack a lot of high number of measurements and to reach the sensitivity, assuming that we have a spatial resolution in the readout of 10 nanometers, which correspond to what we can reach with the current available CCD camera we use. We can reach 1 sigma sensitivity per square root of days of observation. Just for comparison, let's imagine that in 2 years we can run a new generation laser. The name is Atlas. It's in Czechia, and the energy now is not 2.5 but 30 joules. It's still femtosecond pulse at 10 Hz repetition rate. In this case, of course, the signal is higher, 0.2 nanometers, and we can reach 1 sigma sensitivity within 10 minutes of running, which is now very realistic. So let's summarize the goal of this project. The goal parameters. It's an extension of spatial resolution in the readout of 10 nanometers and a waist that focus as small as possible with the goal of 5 micrometers. So in the last few years, when I say few years, already in 5 years, Jeremy, PhD now in your lab, did an internship with us at that period when we started the prototype. So we, during a long ANR program, we developed a DeLLight prototype, and I will show you now the DeLLight pilot experiment in order to validate all these parameters and to validate the method. So let me show you here a picture of the current experiment. You see it has changed now today. Here is the vacuum chamber of light. It's all about 1 meter long, 50 centimeters. Inside here in this part, there is the interferometer, the Sagnac interferometer. With a picture here, you can see the beam splitter, you see very well, and the 2 opposite mirrors and the 2 optical lens, and with the interaction area here. And the goal for this pilot experiment, I will show you the result, is to validate the method by measuring deflection of light by light, but not yet in vacuum, but in standard medium, optical medium with air. The simplest gas we can use. Of course, at very low energy, not at 2.5 joule, but at microjoule energy. So first, the extinction factor, I show you very briefly typical image we have in the readout interferometer. Readout with the CCD camera. And when you, after aligning the Sagnac interferometer, you observe that 2 opposite spots here due to the back reflection on the back side of the beam splitter, and in the middle, nothing. And showing a very strong extension and very good alignment of the interferometer. For the back reflection here, 10 to the -4, because there is some anti-reflective coating on this beam splitter, very efficient one, but we are so sensitive now. And here, this zoom. So we increase the intensity of the camera, and you see here some residual noise. ring due to diffraction and defect of the shape of the mirror of the optical lens. And in the middle, some you do not see very well, but there is some hot spot due to some defect of roughness defect of the optical surface of the interferometer. So by adding what we call a spatial filter in the external, in the dark output of the Sagnac, we filters all the diffusion and diffraction. It's a standard technique. Then we can remove all these diffusion patterns and obtain the dark output, an excellent alignment with no noise, no phase noise anymore. And this corresponds to an extension of 3×10⁻⁶, which is the goal of our project. So here it's details. So first on here it's when we use all the spectral filter of our laser pulse. It's a very short pulse, 30 femtosecond. It means, in this case, due to Heisenberg uncertainty, it corresponds to a large spectral spectrum of about 40 nanometers large. So here, to reach this extension, we had to select about 5 nanometers of this spectral bandwidth. If we open and use all the spectral filter, then the beam splitter is not perfectly symmetric anymore, and we see some light which appear in the dark output at the level of 6×10⁻⁵. So first lesson is that we see that we are able to reach 5×10⁻⁵. One of the parameters. We are still limited by this back reflection. So we are now developing a new beam splitter, thicker and with a better anti-reflection coating in the back side in order to reduce this back reflection, in order to increase incident entering in the lab, because then we need to measure something. So the second point, you remember, the second very important parameter is the spatial resolution in the dark output. This spatial resolution is limited by the ultimate resolution, the shot noise, due to statistical fluctuation of the number of photons detected on the CCD. And then, of course, if we do a measurement, we are at first level limited by the beam pointing fluctuation of the laser, which fluctuates at the level of few tens of micrometers. And the last is the phase noise fluctuation, which is the last limitation. So in order to measure that, image, as you can do, current beam that we have, they are limited by back reflection. So in order to measure something, we must reduce the extension and try to not work anymore at very strong extension. But we reduce it to 5×10⁻⁴. So the price is we are going to have a lower amplitude. But at least doing that, you can see you are here start measuring spatial resolution, the possible signal. So we did that. Actually, there are two ways. Either we introduce the beam splitter is perfectly symmetric for a given polarization. So what we do is rotate very slightly the polarization of our incident beam light. And by doing that, we introduce small asymmetry in our beam splitter. And the second way is beam splitter is optimized at 45° incident angle. So we rotate by 1° only. And in this case, the coating of the filter is not symmetric anymore. And again, we rotate in order to online. So in the first, we can show that in the first method, it corresponds to an amplification very small, no small amplification anymore. And in the second way, by rotating the beam splitter, we obtain what we call the high amplification regime, an amplification here at 25. Second point now is to define a barycenter, because we are looking for so we define barycenter and using also the reference. Well, sorry. Yes, here is voilà. Let me start in the right way. Here the interference signal. So we calculate the barycenter in the region of the and we use the reflection in the backside of the beam splitter as a direct online monitoring of the position of the beam. Because from pulse to pulse, the beam shot, there is some pinpointing fluctuation. And it fluctuates. So this reflection is used to measure the pinpointing fluctuation and to correct and suppress it from the direct interference. So here there is a simple sketch. Sometimes we alternate from the measurement to the front off, then to the front on. Yeah. Front off, for instance, here, in blue, what we call the signal from the reflection of the backside of the beam splitter, which is a direct image of the incidence beam. And then for the successive laser shots on measurement, for instance, the beam has fluctuates, so the position fluctuates, so we measure it in the back. Plus, there is a DeLLight signal, a deflection signal, or interference signal. That's the signal we are looking for. So using the back reflection, we correct the pinpointing fluctuation, and then we extract the signal. Yeah? So here is an example of successive off and on measurement at 10 Hz laser repetition rate. With the off measurement, the correlation of the interference signal position barycenter versus the reflection signal. So there is, of course, a perfect correlation. And then we use this correlation and apply it to the on measurement. And we extract, you see here, a shift which corresponds to the deflection signal we are looking for. So before showing you such positive signal, what we do first is to do that without pump. It means we are running now in Sagnac interferometer. We alternate laser shot without pump. So it's what we call off minus off. And check that we have 0 and what is the spatial resolution. So here it's an example of 14 successive laser shots, 7 minutes accumulated with the off, also the old laser shot, followed by the even off laser shot. And we do exactly the same analysis procedure and apply the correct interpretation, wrong on, off measurement. And then we extract the signal. And here is the signal, we expected the deflection signal versus time on off minus off measurement number. And so we check that the average value is compatible to 0 as expected, and with a spatial resolution of about 30 nanometers. What is this residual resolution is exactly what we are looking for, the CCD shot noise, due to the residual fluctuation of the statistic fluctuation of the photons read on our CCD camera. to show you that, we developed a dedicated bench, a test bench, to measure using a standard laser diode the resolution, intrinsic resolution of the camera, fitting the pulse again in two different pulses in order to simulate what we are doing with our interferometer and correct the pinpointing fluctuation in the two signals, measuring the final ultimate spatial resolution limited by the shot noise or quantum noise of the CCD camera. And we verify that with our current CCD camera, the measured shot noise is 28 nanometers, so in agreement with what we measure. And with a better camera, which is still in our furniture but not yet used, we can measure a resolution of 13 nanometers, which is in agreement with the expected goal parameter of 10 nanometers. Just to show you here that actually, when I said, okay, we reach the shot noise, it's almost true. It's true, but for a very limited region of interest to calculate the barycenters, a small region of interest. And if I show you again here, it depends on the size of the region of interest. And larger is the region of interest, better you will contain the deflection. And the inverse, use a small region of interest, you introduce some bias and you reduce any possible deflection measurement. So you need just a large region of interest. But the problem, if you use a large window analysis, you integrate the noise and the phase noise from the interference signal. And that's exactly what we observe here, is that the spatial resolution as a function of the size of the ROE. One here in units corresponds to a region of interest equal to the full width half maximum of the Gaussian pulse. So as soon as spatial resolution is getting worse, and here at 2 full width half maximum, which correspond to an efficiency of 70–80%, the resolution is about 100 nanometers. And that's actually due, and the quantum noise here is almost constant. And that's actually due in agreement with the simulation where we simulate mechanical noise from our optical elements in the Sagnac due to rotation vibration. And it corresponds, this noise measure corresponds to a fluctuation of about 50 nanoradian RMS, which is small, but too high in our case. And the main reason is, so of course, it's always like that. You discover noise high unit, and it's need because we are the mechanical isolation is today very poor. We are working in a very poor condition, and so now the new step is going to install it in a clean area by some dedicated isolation, mechanical isolation. So here that's a typical sketch of the way we want to improve the mechanical isolation. And secondly, thanks to this measurement of mechanical noise, we realize that we are now developing a new way to measure online simultaneously this phase noise by doing similar to the pinpointing suppression and by splitting the probe beam in two successive probe beams separated by about 10 nanoseconds only, and to measure simultaneously these two interference signals in two different CCD, and the second is sensitive only to this phase noise. So the idea is to measure directly, simultaneously, the interference signal plus phase noise, and the phase noise only, and suppress it. So these 2 points are now in development in our cell. The last point is to check that we are really able to measure a deflection of light by light using this method, interferometric method, and with a pump probe experiment. And so during almost 2 years, develop this pilot experiment in order to measure that in air, in a gas, in the air, using, as I told you, nonlinear optical Kerr effect of the change of index by the laser pulse itself. So basically, it's exactly we use the current pilot experiment, but either pumping the vacuum chamber, we keep it in air at atmospheric pressure, and the only change is that the pump pulse is not the high intensity pump pulse, because in this case, first we produce plasma and we lose our pulse immediately. There is strong damage in air, but so it's a very low energy pump pulse. The level of 10 microjoules, not 2 joules. And secondly, we interact with the probe by with parallel pump and probe pulse in order to increase the effect. And then we did some measurement in order first to check that we have the signal, that we amplify it, and that this signal varies as a function of different experimental parameters. One very important point here is that I show you again our CCD image in the dark output of the interferometer. So in the middle, the interference signal. As you remember, on the left, the image of the beam from the back reflection on the back side of the beam splitter in order to suppress the beam pointing fluctuation. And on the right, it is also the back reflection of the beam splitter. But the advantage of this one is that it's a direct measurement of the probe from the back reflection on the back side. So this image has been also deflected by the pump. But the difference with the interference signal is that this deflection is not amplified. It's like a standard beam pointing beam deflection measurement. So we have the interference signal with the amplified deflection. On the right, the direct deflection not amplified. And on the left, the image of the direct beam in order to suppress the beam pointing fluctuation at the 0. So again, a picture of the setup. So first, here is a leakage at focus in the interaction area. We first need to be sure that we have a space-time overlap of the pump and probe pulse, which is quite difficult because we have to check at the level of 20 micrometers, and in time, it has to be in time at the level of 50 femtosecond. So we use the focus plane in order to check overlap position, and we adjust the delay of the pump compared to the probe in order to observe interference. And as soon as we have interference at focus, it means that the 2 pulses are in time and interfere. And then for the space overlap, we move the pump slightly shifted to the probe in order to optimize the gradient, the deflection of the probe. And we can show that the deflection of the probe is a function of this, what we call the parameter impact, as in particle collider. And this deflection is maximum for an impact parameter, which is a function of the square root sum of the 2 weights of the pump and the probe. So first, we optimize the parameter impact. we adjust the time coincidence by observing the interference, and then we can start running and doing some measurements. So here is the result of our measurements. Now we are writing paper to publish such results. Here is the first deflection signal as a function of the intensity of the pump. Increase or decrease the energy of the pump, and we verify that the deflection signal vary as expected. It is linear or an increase as a function of the intensity of energy. In orange, the amplified deflection meter from the interference, and in blue, that's the direct deflection measurement from the second back reflection. So we verify also that the 23 as expected, because we expected an amplification factor of the level of 25. Second test has to measure this deflection signal as a function of the DeLLight time of the pump with the probe. And we can verify that when we scan from a pump before the probe, there is no deflection. And then when the pump is in coincidence, you have the maximum of signal. And then the pump arrives later, you have no more signal anymore. And final test was a signal, deflection signal, as a function of the polarization angle between the probe and the pulse, and the probe. Sorry. And we verified that the signal is maximum when the probe and the pump are polarized parallel. And when the polarization are perpendicular, the signal becomes null. So let's try to, I don't know why we see so what next for this from this all these results? So first now we as I explained, we need first to reduce the noise, the phase noise due to mechanical vibration. So that's what we are doing now for next year, I guess, because it takes time for metrology, nautics, everything takes time. And then in parallel, developing new beam splitter to improve the performance of this beam splitter. For all the measurements I show you in air, we have a waist at focus, a width, transversal width of the level of 25 micrometers, and we need to decrease the width at 5 micrometers. So we need improvement parameters. And then finally, next year, we will plan to start first measurement in vacuum with high energy. And then again, the goal is to start running and accumulate some data at Orsay with the LASERIX facility. And then, if results are good, but excellent, then we'll be able to go in order to run with the same interferometer, but with an energy about 20 times higher. So conclusion. Positive measurement of light element will be, I think, personally, that's the reason I work hardly on that, will be a major result because it will demonstrate that the speed of light in vacuum can be reduced. For me, 7 years ago, it was very surprising when I discovered that. And I mean, reduced in the classical sense, on macroscopic scale for an optical phenomena in the presence of electrons in electromagnetic. So we can normally change the vacuum and the speed of light intense laser pulse. Just again, this parallelism saying that in electromagnetism, we have a theory. The name is QED. We have a theoretical prediction of this deflection. Unfortunately, nobody observed it. And in gravitation, that's the inverse. We have already observed it, the deflection. We have also observed the deceleration, the Shapiro effect. But there is no physical theory, I would say. There is a geometric theory, but there is no theory of the link of this phenomena with the quantum vacuum. But when I say no physical explanation. So there is, I confess, it's a challenging project, not to say a hard project. But so far, there is no showstopper. And every time, of course, we discover new noise, but we know the reason of this noise, we know how to reduce it, and so on and so on. And so we are confident. But, and that's my last point, that we need new collaborators. They are welcome. And because there are many different points to study, either in optics, but not only in optics, in vibrational mechanics, in analysis, acquisition, in control command, and so on. And sure, it's a project for which we really welcome new collaborators to work on this adventure. So we need you. You chose the guy who asked that. Voilà, thank you very much.
Are there questions? Please, could you speak up so people remote could catch by my microphone? Thank you.
So thanks for the presentation. It was really interesting. I have like 50 questions. So I know there are some disagreements in terms of this, but one way to think about the Casimir effect is modification of the vacuum. The vacuum. So can this also modify the speed of light? So if you think about an experiment when you make fast light within 2 neurons,
yes. So as you said, as you point, Casimir effect is another effect where you modify. It looks like you modify the vacuum at the microscopic scale, and you suppress some modes of the quantum of the electromagnetic fields, vacuum electromagnetic fields. So I would say that's the inverse of what we do here. It's because you suppress some modes. It means you pump. It's like you pump the vacuum. And actually, you're right. There is some paper where they try to calculate inside in the frame of QED a change of the speed of light. Unfortunately, it's very small because you change very slightly. You suppress some modes, harmonic of these modes, which is almost nothing. So they have successfully measured the force, the Casimir force, interpreted as that. I think so, but for the speed of light, it's very small. And there is another paper who calculated the change of the inertial mass of the electron, also crossing through a Casimir plate, and they expected also some change of mass, inertial mass, but it's a very tiny effect. So here, it's like the inverse, at least in the QED frame. When you add external field, it's like you add some E plus E minus fluctuation pairs, and so you do not pump the vacuum, you fill the vacuum, and that's the reason QED predicts a reduction of the speed of light, not an increase of the speed of light. In Casimir, that would be an increase. Here, that's a decrease of the speed of light. But maybe that's the inverse. Maybe we measure an opposite deflection, Meaning that actually, no, there is an increase and QED is wrong at very intense field because there is some saturation effect. In QED, there is infinity, but nobody knows actually. There is maybe a level of saturation effect, and then you saturate, and so we see. Which is, it looks to be the case in an optical medium, gas, for example. When you increase the external field, you increase the index by the optical tail effect. But then at very high intensity, that's the inverse. You have some saturation effect. And you have second order of nonlinear optical tail effect, which becomes negative. And then the light increases again.
But I imagine that in
so in vacuum, normally QED say that there is no saturation and should only increase, decrease the speed of light. So the 14 other questions, no?
Yeah, no.
Please.
Well, so is it, well, you're saying that when you have strong magnetic field, there is modification of the speed of light. It could be applicable around the magnetars in the near the environment of the magnetars, where the light could be modified, where the speed of light could be modified, and then the emission of the magnetar could be modified too, I guess.
Yes. In close to a pulsar, as you said, we have some magnetic field at the level of 10 to the 5, 10 to the 6 Tesla. And in that case, the nonlinearity, vacuum nonlinearity, becomes non-negligible. And there is a claim from astrophysicists who say that they observe some birefringence, vacuum birefringence from the emission of pulsar. This paper has been published like 4 or 5 years ago. And it's, well, first, it's a very indirect measurement. It is a criticism because they try to push everywhere. It's model dependent and so on. So I don't know. I'm not able to judge about that. I remember at that time Arash gave us a sort of personal referee saying, showing us some very limitation of this analysis. So nobody knows exactly if it has already been observed or not indirectly from pulsar.
Okay, thank you.
Yeah, maybe to complete your answer, there are some expected effects in terms of change of polarization angle, close to magnetars, surface or pulsars. These effects are difficult to disentangle from other ones which also change the polarization. So, but there are some predictions. Of course, you expect these effects.
Okay.
Other questions, or shall we thank? Please go ahead.
I have one. In fact, I don't fully understand the impact of the angle you put on the pump with the main arm of your interferometer. Is there a way to operate it normally to the arm?
I know, to be sure to understand your question. Here from this sketch, from
Yes.
So which angle are you speaking about?
It's the pump.
Okay, yes. So now, the effect should be maximum when the probe and the pump are counter-propagating. I will explain after why counter-propagating and not co-propagating. So it's maximum in counter-propagating, and it's even better because you can really integrate the effect. Unfortunately, it's not possible. Well, so far we have not found any trick to be totally
counter-propagating. And we need a tilt angle in order to allow the pump pulse to propagate and reach the interaction area focus
without touching anything.
And today the setup is designed for a tilt angle at 15 degrees.
And all the result I show you for the expected signal of sensitivity is at 15 degrees tilt angle.
And at 90 degrees.
At 90 degrees, it's already quite strongly reduced by, I remember well, by a factor of 5 or 4. And then it becomes null, 0, when the probe and the pump are co-propagating. And the reason is that if we look at the polarization and magnetization from the vacuum, calculated by Heisenberg and Lair, Schwinger also. Actually, this expression is given by Schwinger. The expression from Heisenberg and Lair is
very difficult. There is integral and so on. It's pure Germanic theorist.
And here Schwinger gives
a readable
formula. Anyway, as you see, the polarization of nonlinear polarization of magnetization of the vacuum is proportional to the two invariants, Lorentz invariant parameter E square minus B square or E scalar B. It means for a counter-propagating probe and pulse, these factors becomes well, this factor is equal to 0 and this factor also. And when they are counter-propagating with rotation of the polarization, this factor becomes non-null. So, and to say differently, if you use electromagnetic wave as intense as you want, very, very intense, it will never modify the vacuum for itself. So you need really a coupling of two fields with at least one of these two parameters which are non-linear. So that's the reason actually we need a pump plus a probe. And when I say to simplify, the pump is focused and imprint an optical gradient in vacuum, alone it's not very true. it needs the coupling of even a low probe pulse, which is strange, but it's saying that. Maybe everything is wrong, but mathematics say that.
So, if I understood it well, with your current setup, you need to include this spectral filter to have a good sensitivity, a good amplification. How much energy you filter from this?
Yeah.
For this for the future or without a filter?
Voilà, c'est là.
Yes, here actually, delta is the value, the difference from the reflectivity and transmission parameter of the beam splitter. It's 50-50 plus delta minus delta. Actually, so they developed some dielectric coating in this beam splitter, optimized to work for polarized light at 45 degrees and for a given wavelength. And which is normally they do that for monochromatic. Those people, especially for interferometry and electrodynamics, they use continuous length at a monochromatic value. Here for femto pulse, that's much more difficult because we have a spectrum which is the width is about 30 nanometers, even actually today it's 45 nanometers. So we need to optimize this coating for quite large spectrum. Well, 30 nanometers is quite small, but for in optics it's large. And and actually these parameters has to be as small as possible, but there is some shape typically like that. So what we use is we add interferometric filter, which selects here 5 nanometers, and we scan by rotating this filter. We scan the spectrum, and we really see that the extinction, residual spots decreasing or increasing, depending on where we are on this blue curve, this asymmetry parameter. So that's the reason of development of a new dedicated beam splitter in order to have such parameters as low as possible on the full spectrum, in order to accumulate all the light, which is important to reach the shot noise, because we need a lot of photons. Voilà.
Other question? All right, so let's thank Xavier, Sarazin once again. Thanks to all.